Hello students, welcome to this lecture in which we're going to talk about some applications of integrals. So we kind of step away a little bit of triple integrals, but we're going to come back to those. So first we're going to think about density and mass. So suppose that the lamina, so thin plate pretty much, the lamina with variable density, with variable density. So what is the density? Density is units of mass per unit area. So lamina with variable density occupies a region D. Occupies a region D in xy plane. So we have something like this. We have xy plane, and we have some lamina over here. All right, so this is a region D, and if we take a little piece over here, maybe a little square, all right, and we have a point over here, xy. So let rho of xy be the density, and rho of xy is a continuous function. On D, on the region D. So what does it mean? This implies that the limit of delta m over delta a is our rho. And what is what? In this formula, delta m is the mass, and delta A is the area of a small rectangle. That contains xy. And the limit is taken as the dimensions delta, the dimensions of the rectangle approach 0. So what do we mean? We mean delta x goes to 0 and delta y goes to 0. So that's our initial approach. And what do we need to do now? We go through our standard procedure. We take the region, we subdivide it into the bunch of rectangles. So we take our region and we're going to subdivide it into a bunch of rectangles. Maybe different color. So all right. So one of the lines probably goes on top, and I'll undo that. So suppose this is my region over here. Okay, so this is my region, and so inside of the region over here, we have a point like always x sub I sub j star, y sub I sub j star. So that's our point, and the region itself is ri sub j, ri sub j. So we can say that to find the total mass, M of this lamina we divide the region into subrectangles R sub I sub j, right? And consider that the function rho of xy is 0 outside of D, outside of the region D. So if we choose the point x sub I sub j star, y sub I sub j star in R sub I sub j, then the mass of the part of the lamina that is in R sub I sub j is approximately rho of x sub I sub j, y sub I sub j star times delta A. Why is that? Because of this, right? Because of this. So it's approximately. So if we remove limit, then it's going to be an approximate sign. And so if we multiply both sides by delta A, we get approximately the delta M. All right. So where delta A is the area of R sub I sub j. Now we add all of these masses. Now we add all of such masses and we get an approximation for the total mass. So M is approximately the sum when I goes from 1 to n, and the sum when j goes from 1 through m of rho of x sub I sub j star, y sub I sub j star times delta A. And we take a limit. We take limits as n goes to infinity and m goes to infinity to make the spaces small. So m is equal to the limit of n and m goes to infinity of sum I goes from 1 through n, sum for j goes from 1 through m, rho of x sub I sub j star, y sub I sub j star times delta A. But this is exactly the definition of the double integral over the region D, where our function is rho, so it's rho of xy dA. And that's how we got into this integral, right? And it doesn't have to be only density. So sometimes in physics we can think about electric charge. So electric charge could work the same way over the region D. So instead of density, we can use electric charge over the region D the same way. So the total charge is Q is equal to double integral over the area D of sigma of xy dA where sigma is density, sigma is charge, electric charge distributed over D. So it's measured, sigma is measured in units of charge over area. All right, so let's do an example. So in this example, let's we have a charge that is distributed over the triangular region D. Triangular region D, so that sigma of xy is equal to xy, and the region is given by this picture. So this is 1, this is 1, and this line over here is y equals 1 minus x, and y is equal to 1, and this point is 1 and 1. So this charge is measured in coulombs per square meter. So coulombs per square meter. All right, so C over m squared. We need to find the total charge. Find the total charge. All right, so we know that the total charge is a double integral of the region D and we have sigma dA. All right, so let's think about our y. Our y is changing in this direction over here. So it goes from this line to this line over here. So it goes from 1 minus x to 1, and x changes from 0 to 1. And we have xy dy dx. So we have an integral from 0 to 1, xy squared over 2, from 1 minus x to x dx, which is equal to the integral from 0 to 1. We have to plug in 1 first, so we're going to get x over 2. And then we plug in 1 minus x, so it's going to be x times 1 minus x squared divided by 2 dx. All right, so maybe it's wise to simplify this expression. So we can factor x over 2 out. So we're left with 1 minus, so we square this expression, so it's 1 squared minus 2x plus x squared, but since they have the same common denominator, we can just distribute the minus. So we put plus and we put minus. All right, so this one and this one adds up to 0. So we're left with integral from 0 to 1. So we multiply out this 2 and this 2 goes away. So we have x squared minus x cubed over 3 dx. X cubed over 2, sorry. X cubed over 2 dx. So we integrate, so we're going to get x cubed over 3 minus x cubed, x to the 4 over 8, 4 times 2, evaluated from 0 to 1, so it's 1/3 minus 1/8. So what do we get if we have a common denominator? We multiply by 8, and here we multiply by 3. So we have 24 on the bottom, 8 minus 3, so 5 over 24 coulombs, right? 5 over 24 coulombs, that's our total charge. So probably a good place to stop this lecture, and next time we're going to talk about center of mass.